9.5 Collisions in two dimensions. The outline of this video is as follows. We will begin by extending the law of conservation of momentum to two dimensions, which is essential for analyzing collisions that are not head-on. This leads us to the topic of glancing collisions, where we will see how momentum is conserved independently along both the x-axis and the y-axis. We will then differentiate between elastic and inelastic collisions in two dimensions, noting the key role of kinetic energy conservation. Following this, we will establish a systematic, step-by-step problem-solving strategy to help you tackle these scenarios confidently. Finally, we will apply this entire framework to a detailed worked example involving a two-dimensional elastic collision. We can now extend the principle of momentum conservation to collisions in two dimensions, which is essential for analyzing any collision that is not a simple head-on impact. Because momentum is a vector, if the total momentum of an isolated system is conserved, then its components in each direction must also be conserved independently. This powerful idea allows us to split one complex two-dimensional problem into two simpler one-dimensional problems, one for the x-axis and one for the y-axis. The first equation on the slide expresses this for the x direction. The total initial x momentum equals the total final x momentum. The second equation shows the same independent conservation for the y direction. A classic example is a game of billiards. When two balls collide and scatter, we can analyze their motion by separately conserving the total momentum along the length of the table and the total momentum across the width. In short, one vector conservation law gives us two independent scalar equations for collisions in a plane. Let us apply the principle of momentum conservation to a common two-dimensional scenario called a glancing collision. In this setup, a moving particle, m1, strikes a stationary particle, m2. After the impact, they scatter at angles theta and phi, respectively. To simplify the analysis, we align the x-axis with the initial velocity of particle 1. This is a very useful strategy because it means the entire system has zero initial momentum in the y direction. Now we can write our conservation equations. First, for the x-axis, the total initial momentum, which comes only from particle 1, must equal the sum of the final x components of momentum for both particles. These components are calculated using the cosine of their final angles. Second, for the y-axis, the initial momentum is 0, so the final y momentum must also sum to 0. This means the upward momentum of particle 1 must be perfectly balanced by the downward momentum of particle 2. This component-based approach provides two independent equations that describe the outcome of the collision. The type of collision is crucial because it determines how many equations we have to describe the final state. Let us first consider an elastic collision. Here, kinetic energy is conserved, which gives us a third equation relating the speeds before and after the collision. This is a big help, but we still face a problem. We have our two momentum equations and this one energy equation, for a total of 3 equations. However, there are 4 unknown quantities to find: the two final speeds and the two final angles. Therefore, to solve the system completely, we need one more piece of information about the final state. Now, if the collision is inelastic, kinetic energy is not conserved. This means we cannot use the energy equation. We are left with only the two momentum conservation equations, but we still have the same 4 unknowns. This makes the problem indeterminate without significant additional information. The key takeaway is that conservation of energy in elastic collisions provides a powerful third constraint, but more information beyond the initial conditions is required to fully solve a two-dimensional collision. To solve two-dimensional collision problems effectively, we will use a structured, 4-step approach. This method helps to organize the information and ensure all physical principles are correctly applied. First, conceptualize the collision. This means drawing a clear diagram. you should establish a coordinate system, and it is often very convenient to align the x-axis with one of the initial velocity vectors. Be sure to label all known and unknown velocities on your sketch. Second, categorize the interaction. You need to determine if the system of particles is isolated, which is the condition for using conservation of momentum. Then, classify the collision as elastic, inelastic, or perfectly inelastic. This will tell you whether or not you can also use conservation of kinetic energy. Third, analyze the problem by writing down the equations. The core principle is that momentum is conserved independently in the x and y directions. This gives you two separate equations. If the collision is elastic, you have a third equation from the conservation of kinetic energy. You then solve this system of equations for the unknown quantities. Finally, finalize your work by checking if the results are reasonable. Compare your calculated final velocities to your initial sketch to see if they make sense. This systematic process turns a potentially complex problem into a set of manageable steps. Here is an important warning regarding a common mistake when solving collision problems. For one-dimensional elastic collisions, we found a very useful relationship for the relative velocities. This equation states that the quantity v1 initial minus v2 initial is equal to the negative of the quantity v1 final minus v2 final. This formula is a powerful shortcut, but it is derived under the very specific condition that all motion occurs along a single straight line. When a collision happens in two dimensions, the velocities are vectors that can change direction, having both x and y components. The simple one-dimensional relative velocity equation cannot account for this complexity and is therefore invalid. Attempting to apply this equation to a two-dimensional scenario, such as a glancing collision between two billiard balls, will lead to an incorrect result. The critical takeaway is that this relative velocity equation is a tool exclusively for one-dimensional elastic collisions. Let us apply our understanding of momentum to a common real-world scenario: a collision at an intersection. In this problem, we have a car with a mass of 1,500 kilograms traveling east at 25 meters per second. It collides with a 2,500 kilogram truck that is traveling north at 20 meters per second. The key detail here is that the vehicles stick together after the impact, moving as a single piece of wreckage. Our goal is to find the final velocity, which includes both the speed and direction of this combined mass. To analyze this two-dimensional problem, we will set up a coordinate system where east is the positive, x, direction, and north is the positive, y, direction. Because the vehicles stick together, this is a perfectly inelastic collision. We will model the car and truck as an isolated system, which means their total momentum is conserved. Therefore, we will solve for the final velocity by applying conservation of momentum independently for the x and y components. To solve this two-dimensional collision, we apply conservation of momentum separately to the x and y directions. First, in the x direction, the initial momentum comes only from the car. The final x momentum is the combined mass of the wreckage times its final velocity component, which is the speed v, f, times the cosine of the angle theta. Similarly, in the y direction, the initial momentum comes only from the truck, and the final y momentum is the total mass times v, f, times the sine of the eta. We now have two equations and two unknowns, v, f, and theta. A useful trick to find the angle is to divide the y momentum equation by the x momentum equation. This cancels the total mass and the unknown speed, vf, leaving an expression for the tangent of the eta. Plugging in the numbers, the inverse tangent of 1.33 gives an angle of 53.1 degrees. Once the angle is known, we can substitute it back into either equation to find the final speed. Using the y equation as shown, we calculate a final speed of 15.6 meters per second. By conserving momentum in each direction independently, we can solve for both the speed and direction after the collision. Now, let us apply our conservation principles to a classic physics problem: an elastic collision between two protons. In this scenario, one proton with a known initial speed strikes a second proton that is initially at rest. After this glancing collision, the first proton moves off at a measured angle of 37 degrees. Our goal is to find the final speeds of both particles and the angle at which the second proton recoils. Because the collision is elastic and the protons form an isolated system, we know that both momentum and kinetic energy are conserved. We can express the conservation of momentum using two separate equations for the x and y components. The first equation states that the initial x momentum, v1 initial, equals the sum of the final x momenta, v1 final times cosine of theta plus v2 final times cosine of phi. The second equation shows that the initial y momentum is 0, which equals v1 final times sine of theta minus v2 final times sine of phi. Since the collision is elastic, our third equation comes from the conservation of kinetic energy. This gives us that the square of v1 initial equals the sum of the squares of the final speeds. Notice that because the masses of the two protons are identical, the mass term, EIM, has cancelled out of all three equations, simplifying our work. But with these three equations, we have a complete system to solve for our three unknowns. Now we will solve the system of three conservation equations for our unknowns. A powerful strategy is to first eliminate one of the unknown angles, in this case the angle phi. We accomplish this by rearranging the two momentum equations to isolate the terms containing phi on one side. Then, we square both of these rearranged equations and add them together. This is a very useful algebraic trick. Because the sine squared of any angle plus the cosine squared of that same angle always equals 1, this step makes the angle phi disappear from our equations. This process gives us a new expression for the quantity v2f squared. We can now substitute this expression into our third original equation, the one for the conservation of kinetic energy. After substituting, you will see that several terms, like v1 is squared, conveniently cancel out from both sides of the equation. This process leaves us with a much simpler final relationship between the final speed of the first particle, v1f, its initial speed, v1i, and its scattering angle, theta. The equation from our previous step gives two possible solutions for the final speed of the first proton, and we must choose the one that matches our physical situation. One solution is that v1f equals 0. This corresponds to a head-on collision where the first proton stops completely. Since we are dealing with a glancing collision, we discard that solution. We use the second solution, which states that v1f equals v1i times the cosine of the theta. Plugging in the initial speed and the 37-degree angle gives a final speed of 2.80 times 10 to the power of 5 meters per second for the first proton. Next, we find the speed of the second proton using the simplified energy conservation equation. Substituting our known speeds, we calculate v2f to be 2.11 times 10 to the power of 5 meters per second. Finally, to find the angle phi, we use the y component of the momentum equation. We solve for the sine of phi, which gives a value of about 0.799. Taking the inverse sine gives us the angle phi, which is 53.0 degrees. Let us finalize our analysis of this proton-proton collision by looking at a fascinating geometric result. Which we add the final scattering angles together, we find that theta plus phi is 37 degrees plus 53 degrees, which equals exactly 90 degrees. This means that the final velocity vectors of the two protons are perpendicular to each other. As the slide notes, this is not a coincidence. It is a general rule that holds true whenever three specific conditions are met. First, the collision must be elastic, meaning kinetic energy is conserved. Second, the two colliding objects must have equal mass, as the two protons did. And third, one of the objects must be initially at rest. If any of these conditions are not satisfied, the final velocities will generally not be perpendicular. The key takeaway is that for any elastic collision of equal masses with a stationary target, the two objects will always scatter at a right angle to each other. Let us summarize our approach to analyzing two-dimensional collisions. The foundational principle for any isolated collision is that linear momentum is a conserved vector quantity. This means we can write two separate and independent equations. One for the conservation of momentum in the x direction, and another for the y directions. The type of collision provides additional constraints. If we know the collision is elastic, then kinetic energy is also conserved, giving us a valuable third equation that relates the speeds. In contrast, if a collision is perfectly inelastic, the objects stick together and move as a single unit after impact. This simplifies the momentum equations because both objects share the same final velocity vector. Finally, there is a useful special case for elastic collisions. If a moving object strikes a stationary object of the exact same mass, the two objects will always travel away from the impact point at a 90-degree angle to each other. Therefore, identifying the type of collision is the critical step that tells you which conservation laws you can use to solve the problem. Let us wrap up with two review questions to apply the principles of two-dimensional collisions. The first question describes a special case, an elastic collision between two objects of equal mass, where one is initially at rest. Think about what the conservation of both momentum and kinetic energy implies for this specific scenario. There is a unique geometric relationship between the final velocity vectors of the two balls. Your task is to find the angle for the target ball, given the cue ball's angle of 30 degrees. The second question asks you to revisit the car and truck collision from our earlier example. We know this was a perfectly inelastic collision, meaning kinetic energy was lost. To find the amount of energy lost, you will need to calculate the total kinetic energy of the system right before the collision and subtract the total kinetic energy right after the collision. Pausing to solve these problems will help you connect the concepts of momentum, energy, and collision types in two dimensions.